This lecture is on open loop versus closed loop control systems. A control system is a mechanism that alters the future behavior or state of a system. Now, in order to be considered a control system and not simply a change the state system, the behavior or the outcome must tend towards a state that is desired. Control theory is a branch of mathematics that is concerned with the strategy to select the appropriate input. Or, to put it another way, it deals with how to go about generating that outcome. Without control theory, the designer is relegated to selecting appropriate actions through trial and error. Now, all control systems have two basic parts: the system to be controlled, usually called the plant, and an input into the plant. The input acts on the plant, which responds over time to produce a system output. This type of control system is called an open loop system because the input does not depend on the system output. Open loop control systems are typically reserved for simple processes that have well-defined input-output behaviors. For example, a dishwasher is an open loop control system. The goal of a dishwasher, which is the plant, is clean dishes, which is the output. Once the user sets the wash time, which controls the time to clean the dishes, the dishwasher will run for that set time. Now, this is true regardless of the cleanliness of the dishes. If the dishes loaded were clean to begin with, the dishwasher would still run for the prescribed time. Further, if you loaded the dishwasher with 10 plates full of cake, the set time might not be enough to clean them. Another common example of open loop control is a sprinkler system for your lawn. In this control system, the system output is the moisture content of the soil. Again, the user sets the timer, which controls the amount of time to run the sprinklers. And while the sprinklers are running, the plant, which is the grass in this case, is being watered. Again, an open loop sprinkler system would still run even if it was raining outside. For a more complicated example, imagine trying to obtain a constant speed in your car without the benefit of the built-in automatic cruise control. To do this, you wedge a rod between the front of your seat and the gas pedal to depress it halfway down. The output of the control system is the speed of the car, and the input is the position of the gas pedal. Again, the car itself is the plant. The car begins to accelerate down a flat road until the force supplied to the system is balanced by the force of friction. At this point, the car stops accelerating and maintains a constant speed. But what happens when the car encounters a hill or a valley? Without varying the input, that is, adjusting the gas pedal, the car will slow down or speed up and the desired constant speed will not be maintained. This is the primary drawback to open loop control. The input to the system has no way to compensate for variations in the system. Now, to account for these changes, you must vary the input to your system with respect to the output, and this type of control system is called a closed loop control system. Now, in addition to calling it closed loop control, this can also be referred to as feedback control, negative feedback control, or automatic control. For the time being, we'll use these terms interchangeably, although there are slight variations between some of them that we won't address in this lecture. In closed-loop control, you measure the output of the system with a sensor and compare the result against a reference signal. Often this is referred to as the desired state or the commanded state. An error term is generated and then fed through a controller where the error is converted into a system input value. When drawn in block diagram form, it's easy to see why this is referred to as a control loop. The negative part of the negative feedback control term is based on the comparator juncture where the feedback is subtracted. So how does feedback control work in practice? Well, let's take the case of the dishwasher. There could be a sensor that measures the cleanliness of the plates. The reference signal would be some sort of desired cleanliness level that would be set either by the manufacturer or by the user. This desired cleanliness level would be compared to the measured level. An error term would be generated, which would be fed through a controller which would monitor when to shut off the dishwasher. A sprinkler system could also benefit from closed-loop control. The sensor could be a device planted in the soil that measures the moisture content of the plant. Remember that in this case the plant is both the grass and the soil. The reference signal would be a desired soil moisture content. And again, the error signal would be generated, which would then be fed through a controller, and the controller would adjust the amount of time that the sprinklers ran. The sprinklers would then run until the moisture level reached a specified value, and then they would be shut off. For the car with cruise control, closed-loop control would work something like this. The sensor is a speedometer, which measures the speed of the car. The reference speed would be the speed that the car was going when the cruise control was set. Now, assume that the car starts in a steady state position on a flat road. And what I mean by that is that the speed is constant at your desired speed, and also that the gas pedal is depressed the amount needed to generate that speed. For this example, let's say that the desired speed is 100 miles per hour. Therefore, the speedometer would also read 100 miles per hour, and since the measured speed exactly matches the reference speed, the error term is 0. The gas pedal would stay exactly where it is. Once the car encounters the hill, the speed starts to slow. Now the reference speed is greater than the measured speed, and the error term becomes positive, which signals the controller to speed up. If the car encounters a downhill, the speed will increase. Now the reference speed is less than the measured speed, and the error term will be negative. The beauty of the feedback control system is that it is capable of reacting to changes to the plant automatically by constantly driving the error term to 0. I want to leave you with one more thought regarding closed-loop control. If we take a block diagram and assign letters that abstractly represent the various parts of a control system, we can gain new insight into how feedback control is manipulating a system. For example, if we label the reference signal V, and we call the controller some abstract process D, through the plant G, which produces an output we'll call Y, which can be fed back through the sensor H to generate an error term E. We can then reduce this block diagram even further. For example, we can multiply D and G to combine into a single block. To reduce further, however, takes a small amount of algebra. The error signal is the reference signal V minus the output Y times the sensor process H. The output Y is the error term times D times G. Now solve this equation for E, which will give you Y over dG. Now you can set both equations equal to each other, and through a few more algebraic steps, you can solve for the variable Y with respect to V. And since Y is the output and V is the input, the rest of that equation is what we refer to as a transfer function of the system. In this case, the transfer function is D times G over 1 plus dGH. And for those who are paying attention, you'll notice that I forgot to write the V at the end of that equation there. We can now rewrite this back in block diagram form. These two block diagram representations are equivalent of each other. Now, doesn't this new process look a lot like an open loop control system, only with a modified plant? The feedback path has altered the original plant to be something new. And furthermore, the open loop behavior of this new plant has the exact characteristics we wanted from the original plant, namely that it follows our input. Now here's something to ponder until the next video. What are the limitations of feedback control? In other words, can we make any plant G behave like anything we choose just by adding a feedback control system, which is made up of a controller D and a sensor H? One other thing. Do you think in our car example from up above that using feedback control we can turn a Pinto into a Ferrari just by applying more gas? We'll discuss that in a future video.